Thank you for the introduction, and thank you very much for inviting me here. So today I will not talk about the advanced autonomy in complex aquatic environment. So we all know that these oceans are pretty important to us, and actually over 50% of the Earth's oxygen comes from the plant life in the ocean, and also these oceans it is kind of regulate the climate change, like it absorbs more than 30% of the carbon dioxide, buffering the climate change issue. And also, oceans provide us with seafood, minerals, medicines, and also it supports the international shipping. So even though oceans are very, very important to us, but actually now, like we know more about the surface of the moon than we know more about the bottom of our oceans. So actually, like more than 80% of the ocean is not explored yet. So because of the harsh environment, marine robot is the most visible solution to help us further explore and mapping our oceans. On the other hand, so due to the human this activity and also the climate change issues, so oceans are facing a lot of problems like the ice sheet melting, harmful algae blooms, this ecosystem degradation, and the marine litter problems. So again, marine robots can be used to monitor these issues and diagnose, and even further can do the treatment of all these issues. Like maybe we can use robot to decorate the ecosystem degradation and also can collect the marine litter of in the ocean. So, but developing these marine robots are quite challenging. For example, marine environment or oceans are always very harsh. Like this, sometimes we will experience very large current, waves, and wind. All this will make the control very, very difficult. So it requires robust controllers compared to the ground-out flying robot. And another thing that all these marine robots, we need to kind of make sure that it is waterproof. And if it is going to the deep sea, there will be this high pressure issue and corrosion issue, like how we can really design or develop this new kind of material and the design to make sure it is working well. So we always require more special material and design for this marine robot. So another thing is the navigation difficulties. So not like us on the Earth or in air, like we have all the GPS and we can easily localize ourselves. Like the RTK GPS can even reach to centimeter level accuracy. But in the oceans, there's no GPS. And the cameras are also not that effective. Normally, these oceans have a very low visibility, which means the cameras can only see several meters. How we can kind of navigate in a larger horizon or larger scene is kind of difficult. And again, there are some solutions like we might use acoustic sensors, but these acoustic sensors normally very expensive. For example, for this 3D LiDAR or imaging LiDAR, they cost kind of more than like previously it's more than maybe 100K, but now the price is going down, but still like 30K also. So pretty much expensive. So that's also kind of a challenge to kind of get this navigation system ready. So we require more stable underwater SLAM and perceptions for the ocean environment. And other challenges include the communication. So we all have this 5G Wi-Fi that we can use to communicate freely. But in the ocean or under the water, all these RF communication systems will not work. There's no 5G Wi-Fi, and there are some methods normally used, like this acoustic method, But this acoustic method have a lot of limitations. For example, the speed of this communication is very slow, and in some rocky areas or this rush waters, this communication is not that stable. We might need to have some options or complementary new communication systems for the underwater vehicle. Another thing, if you notice, is that most of these marine robots, then their ship design is quite is quite kind of non-optimal. You see a lot of these robots, they are just a rectangle box, and we might need to kind of and also these batteries normally is a big issue. So we always want to optimize this current ocean or marine robot to kind of improve the duration of the operation. And also the propulsions efficiency is pretty low. Normally, if you have a boat and you have a thruster on the boat, this propulsion efficiency is only 20 to 40%. But in nature, these aquatic animals like fish, they can reach more than 90% of the efficiency. So if we can get inspiration from this aquatic propulsion or this balanced wave propulsion, we might need to get more optimized propulsion. So that's another kind of challenge, and we can target for these marine robots. So our lab is focused on this AI-enabled optimal design, control, and coordination for these novel aquatic robots. So we have many three directions. One is that we are interested in developing this AI-enabled robust safe control for field autonomy. So our philosophy is that we always develop this model-based controller, but we might integrate this neural network or learning-based component into the model-based framework to enable more kind of adaptive behaviors. And we always close the loop. We always want to test our robots in the field to make sure that our algorithms are really working in the field. This is one direction. So another direction is that these multi-robot platforms, because oceans are pretty large and harsh, so this robot need to be able to work together to kind of even survive when the water condition becomes worse. So we are interested in this multi-robot platform development, including these different scales of robot swarms, and we sometimes even test in the field to make sure that it can do some real tasks in the format of swarm. So another big area of our research is biosphere research. So we still believe that these animals in the ocean already evolved millions of years. So there are a lot of this optimal design and perception. So we always think about how we can develop some biosphere propulsion system or robots to kind of explore some of the underlying mechanisms or better efficiency of the swimming to kind of enable or get new types of propulsion perception system.
So are you looking at surface robots, underwater, or both?
Mostly surface, but we also interested in this underwater vehicle in the 3D. Yeah. Like we are interested in this flying fish mastery and also some new types of underwater communication systems inspired by some aquatic animals. This is pretty much what we are interested in the marine domain. And today I will mainly talk about this marine like the 2D autonomy on the surface, like the robotic boat, how we can enable this autonomy in the 2D urban environment. And and then I will talk about this modular robot, how we extend our autonomy into this swarm format and enable some flexible applications within using this modular robots. And then I will talk about 3D bio-inspired robotics. Like one example is that how we can develop new communication systems for the underwater community use this new methodology or communication system to kind of complement the current acoustic communication method. So one of the projects we are interested in that how we can kind of developing some autonomous boat for urban environment. For example, like in Venice, Suzhou, or Amsterdam. In these cities, they have thousands of miles of these waterways, but they are not fully functional or not fully activated. And on the other hand, this traffic issue always happens in the cities. So we try to kind of using this autonomous boat technology to transfer some of the traffic on the road to the waterways. In this way, to migrate the traffic issue in these urban cities. So this boat can be used to transport people and transport goods, and also maybe can transport some waste. And sometimes we will put these onboard sensors like water quality sensors to. In this way, we can monitor the water quality in real time, because normally this water is a very sensitive stuff, and we always want to make sure the water quality is good enough for the human living, for recreation. This is potential applications of this autonomous boat for urban cities. But developing these autonomous systems of boat for the coastal cities have unique challenges. For example, this is one scenario you can see that during a summer day in Amsterdam. You see there's not too many rules, and there's a lot of this boat interactions, and sometimes they directly hit each other. The environment is narrow, and you see bridges and buildings. This all makes the perception and the navigation very challenging, and the disturbances from other boats. So this unique challenge is kind of ask us to design more robust control systems of the system. So basically, we have a kind of this autonomy framework for our robotic boat, and it has this decision making and planning system. Also, it can get the object state from the object detection modeler, and then it also has this SLAM algorithms to estimate the robot state in real time, and it then makes the optical free path. And then we have these advanced low-level controllers, including MPC, DRL, and CBF, in this way to make sure that the robot can always stick on the reference path safely and accurately. And this is kind of the full framework. But today, for this section, I will mainly talk about our physical robot design, and also some of the learning-based controllers to enable more accurate tracking tracking control. So for the robot design, we actually have several different versions. We have this 1 meter long boat, we have 2 meter long boat, and this one is a full scale, which is 4 meter long boat. You see that it has this thrusters. We have 4 thrusters, 2 main thruster and 2 kind of a system thruster. And also you see this launching mechanism, which means this boat can autonomous launch to the docking station. It can even kind of connect with other boats to build a larger platform. So you see, this is sensors. We have this camera, GPS, MU, LiDAR, and you see this launching or docking behavior. It has a onboard camera, and then it can detect the docking and finally do the docking autonomously. And then these people or these passengers can kind of get out of this boat safely. This is the sensing package we have. And with all this sensing, we can get this SLAM working, and we can get this perception, like object detection working. And then we will, think about how we can, like after we get this optical free path or reference path from the higher level controller, one design problem is then how we can design controller that is capable of tracking this reference in a more stable, robust way in this natural water environment. These challenges including this changing dynamics, because when we are transporting people or goods, the dynamic will change, and the dynamics also is always oversimplified. So also in the field, there will be a lot of disturbances. How we can account for these disturbances or where we are do the tracking control. These are all the challenges of our control in the urban environment. I mean, we basically adopt this MPC framework. So MPC means model predictive control. So basically, MPC is an optimizer controller, which can optimize a control objective over a horizon or a finite horizon, and iteratively, and it can like accept this cost and system dynamics and the initial state, and also will generate an optimal actions for the next steps. And for example, for our MPC trajectory tracking problem, it is formulated as follows. Here, like Q is the robot state, and QF is the reference state or the trajectory. And we care about both to minimize the error of the tracking error, and also minimize the control effort. And we have the constraints of the nonlinear dynamics and the states, and also the control input. So using this framework, we can actually implement our MPC into our robot. And this is the dynamic model we use. It's pretty much a kind of nonlinear one. We have this state and control, and also the model parameters. So basically, when we build such a dynamic model for our system, we need to do the model adaptation. Like for particular robot, we need to know these unknown parameters like M and D. So we kind of collect a lot of data. For example, we track a sine curve and collect both the status of the state of the robot, and also the control actions, and then we do the model adaptation, and finally we can get a relatively accurate model parameters. And using this identified parameter model or model parameter with the MPC framework, we can achieve a decent tracking performance. But when we deploy it into the field, we still realize that the control performance is not that satisfactory. So it has relatively large tracking errors. So I think about how we can deal with this. The main problem comes with like the disturbances or and also the model inaccuracy. So when again, like when we like deploy it into the real environment, these disturbances and the model inaccuracy just makes the control more or less stable, and the control performance degrade a lot. So first we think about, maybe we can design a robust controller. For example, the cube MPC, if you heard that before, it is kind of a robust MPC framework. The basic idea of this cube MPC or robust MPC is that we based on the nominal MPC controller, we get some feedback from the status or from the state estimation, and then we design a local feedback controller to generate another local control law, and use this local control law to adding it into the nominal control input. In this way, it kind of compensates some of the model inaccuracy and the disturbances of the system. And in this way, we can kind of improve our control performance. This is some of the tests. So we test in a windy day, and you see this. You can feel this wind and also some wave and current. And we test our nominal MPC and also our this robust MPC and compare the performance. And I mean the result is very nice. We found that compared to this nominal MPC, our robust MPC can decrease the errors, the position errors a lot, and even the heading errors is also decreased a lot, like about to 60%. But we still realize that it's not that stable, and it requires a lot of tuning about these parameters. So and also for different kind of this wind or this disturbances, we might need to tune in the parameter. It's not an online or learning based one, or it's not that adaptive, I would say. So we are thinking about how we can add some learning parameters or learning component into MPC framework. So we start to think about what kind of this model uncertainties and the disturbances into in our models. And normally we have three parts of the uncertainty. So one is the unmodeled dynamics. So for example, we use a nominal model to represent the dynamics, but actually the hydrodynamics are more complicated than this first order or second order system. So there will be unmodeled part of the dynamics. And even we have a nominal model and we do the model identification, these parameters are not exactly the same, or there are some parameter mismatch. So this we call this parameter inaccuracies in the model. So these two parts will have errors. Like we can use this F error to represent the model inaccuracy and unmodeled part of the system. And there is also another part called environmental disturbances. Like when you are operating in the field, there will be wind, current, or these waves, or disturbs your system. So how we can kind of model this, or we kind of treat this as a disturbances. So normally a true dynamics of the system includes three parts: this nominal model, this model inaccuracy, and also this environmental disturbances. So we think that how about we use this neural network to learn this F error and also the disturbances together. In that way, we can generate a residual model learning framework. So that's our philosophy. Like when we talk about it, or when we design this learning-based control design, we always want to leverage as much non-system physics as possible. In that way, we can both enhance the stability and also improve the interpretability. And another big benefit is that the neural network is pretty small, so it can make the training even online when we deployment it into the in the field. So we just reformulate our full dynamics of the robotic boat or ASV in such a format. So here is this nominal model, and this if cell here is the residual error, which contains the unmodeled dynamics and the environmental disturbances, and also actually also count for this model mismatch part. So we want to use a neural network to learn this residual error. Yeah, we can use this neural network to learn this one, and then we just formulate a new residual model learning framework for the MPC control. And this is the nominal model, and then we have a residual model learning framework, and we call it online because we first train it in a simulator, and because it's very light. So when we deploy our robot into our lake in the field, we still this residual model learning framework or neural network is still learning the real-time dynamics or the real-time errors in the field in real time. In that way, it can improve the tracking performance much largely. This is the residual model learning framework, and we compare this control performance with three setup. Like one is nominal, the other is offline learning, which means we just do the training, but we didn't do the online learning. And this is the online learning one of our MPC. We can see that in most cases, this online learning MPC have a better control performance compared to this nominal MPC and the offline MPC. We still, I mean, feel like currently this current framework need more safety guarantee. So we are adding a CBF, control verification modular, onto this MPC. In that way, it can further control the control actions and to guarantee the safety of when we are controlling a system. So we further kind of develop such a safe MPC framework to kind of further enable or improve the control performance will ensure the safety of our system. And this is some of the simulation first. Let's see, like we have test with model inaccuracy of the system, and similarly you see that in we compare with the nominal MPC, and we also compare with the MPC CBF, which means there's no learning part, but there is a learning MPC, MPC CBF, and also learning-based MPC CBF. Yeah, we test this model inaccuracy, and also we test with environmental disturbances. In all these scenarios, you will see that this learning-based MPC CBF framework have a much larger much better tracking performance, or has a much less tracking errors compared to the nominal one and the MPC CBF, traditional MPC CBF framework. And we even compare it with this combination of this model inaccuracy and the environmental disturbances. They all like in these scenarios, this learning-based safe MPC control have a much better tracking performance. Finally, we even deploy the system into the lake and test it in the field, and we have the similar result. So again, compared with this nominal MPC and the nominal MPC CBF framework, our learning-based MPC CBF framework has better tracking performance. That's some exploration about our learning-based, or we integrate this learning modeler into our MPC framework. But moreover, we also think about how we can purely using this reinforcement learning framework to replace the MPC-based or model-based one, see whether it also have kind of interesting result. So we are exploring about this DRL control for the tracking of control of the system. Because we believe that this reinforcement learning have a potential to kind of unlock some of the capabilities of the better tracking performance. So again, we first build such a simulation environment, and then we design our reinforcement learning as a creative architecture framework, and then we design the reward for action. We also actually in the simulation we have the model-based disturbances. So in this way, we can training our DRL in the simulation first. After we do the simulation, do the training in the simulation, we directly deploy it into the field again and compare it with nominal MPC. And I mean, interestingly, you will find that this tracking errors of the DRL controller is mostly smaller than the MPC. But a big trade-off is that if you compare with the MPC control forces or control effort, this DRL control efforts are much larger than the MPC control effort, which means it integrates some, or it evolves or develops some strategy that can lower the tracking the tracking error, but the control effort is much larger than the MPC control effort, which means the control action or strategy actually is not optimal in terms of the tracking effort. In some reasons might be like the simulation environment is not that high fidelity, or some other reasons we still under exploration. So after we have all those perception, SLAM, and the control modeler together, we can have this water taxi demonstrating in the Amsterdam canals, and also we can demonstrate how we can use this autonomous boat to transport some waste. And here you also can see from the robot perspective how it can see the environment, map the environment, and also identify the obstacles online, and do the object detection and avoidance in real time. And this is some of the sensors like the 3D LiDAR, RTP, GPS, camera stuff. Okay, this is pretty much the first project about this 2D autonomy in the urban environment. And then we are thinking about how we can have some swarm behavior to unlock some new applications. Okay, by the way, like we have some spin-off of this project. There is a startup happening in Europe, and we are developing this electric 3D printed ferry for large scale kind of this local like this tourist transport. So now let's switch to the swarm robots, like how we can develop these swarms or self-reconfigurable modular robots for the marine environment. The basic motivation is that a lot of these cities, like this coastal city, they do not have enough bridges. So for example, during rush hours, if we have enough bridges of the in the cities, it can decrease the traffic jam a lot. So we are thinking of how we can build these self-assembly bridges for these cities during rush hour. In this way, it might kind of a big benefit for these coastal cities. And also, it can have some temporal stages and to enable some this kind of temporal activities. And also in nature, there are some fair ant. I mean, during flood, this fair ant actually they can self-assembly together to kind of survive in this flood period. And also for this self-assembly robots, actually there's several groups already have research on this, like the Martin's boat swarm, and also we also worked on this shape shifting with 3 robots, and also the Martin's group have this boat swarm stuff. But some gaps about this self-assembly robot in the aquatic area is that all these control systems are centralized. So, and also most of these robots, they do not have a brain. Like all the algorithms are run outside or a remote computer. And even the sensing, there's no sensing modular here. Normally, we use the motion tracking system to get the system working. So I think about how we can develop some fully autonomous system with largely distributed algorithms to enable this interesting or more autonomous swarm behavior or self-assembly behavior. This is some of our like design of the mini boat. So it has simple sensing and localization, and has onboard control and coordination, and the algorithm is largely decentralized. And also the self-assembly is in parallel. And we have this test about our launching. Here you see that our launching system have a very large error tolerance. This is our hardware design, and then we kind of develop also the algorithms of our system. Like this is the algorithm of our swarm or self-assembly system. I will not go in details. The basic idea is that we can kind of have this decentralized algorithm to do the gathering, and we have some centralized algorithm to fix the imperfection as the last phase, and then we can finally have assemble the shape, and it can do some reconfiguration and have a new shape, and also do some collective transportation after assembly even. And we test our systems in such a scenario. Like we have these acoustic beacons to help localize the robot, and we have the MU on board to together have a better estimation about the robot state, and we finally have such a experiment. Like there's 8 robots and randomly distributed on the water surface, and then this robot will can do the negotiation and finally they can form a square and then they can delench and reconfigure to another shape. So in most of the phases, these algorithms are decentralized, except for some imperfection fixing. And then it can move it together as a unit. So yeah, this is pretty much the Swarm stuff. Some of the ongoing work of this research is that we are think about how we can make the robot even smaller. Like we are developing this centimeter level swarm robot. Target is 100, and then we can test this swarm behaviors in a larger scale and do the self-assembly and navigation. And this is some basic initial or preliminary results. Like we can have 3 robots do the self-assembly and the reconfiguration in a swimming pool.
All the robots in the swarm interchangeable?
Yes, so they don't have any ID, so it's interchangeable. Okay, so now let's switch to the bio-inspired robotics. So we always think that, as I said, we want to kind of so to do better design of our current vehicles, to do more efficient propulsion of our current vehicles, and to maybe even kind of improve or get some new perception and communication systems inspired by the aquatic animal. So one example is that this communication system. So as I said, communication system or communication underwater is pretty difficult. Even though like we are developing this different kind of this robotic fish, and we can have very fancy kind of this skills about this robotic fish, but even in the pool, it's hard to control it for this small scale robot. So I mean, as long as it's kind of under the water, even like 1 centimeter, it doesn't lose control. So this traditional like acoustic, they are very large. This system. So we are thinking about if we can develop a kind of more stable and interesting computer system, it might be helpful to this small vehicle application and research. There are like normally 2 methods in the literature for underwater communication. One we call acoustic communication. I guess this one is very common. And for the acoustic, again, it's normally very large and expensive and not suitable for this small robot. And also, as I said, when it is in some rocky areas or in some confined space, the performance is not that good. And there are optimal optical communication systems like light-based communication. But again, it always requires nice kind of alignment. If it is loose side, then the communication also will not be guaranteed. And in the real environment, the water is not clear. So these optimal optical communication systems will have a lot of these issues in real application. And yeah, on the other hand, we find that in nature, there is one category of fish called weakly electric fish. So this weakly electric fish, they can generate electric field around its body. So actually, between its tail and head, it will generate a kind of like voltage, and then using this voltage difference, it will generate some electric field around its body. In this way, it can encode and decode the signal through this electric field in the water. So based on this phenomenon, we kind of do some model abstraction, and we abstract it as such a model, and then we do the mathematical derivation of the system and develop such a model, and then we design the circuit to implement such a bio-inspired communication system, and then we design the board finally integrate this electrical communication system into our robot and test the performance. And like we test in different scenarios with still water, flowing water, water with obstacles, and also natural waters. And they are all have a very nice performance. Like we found that this communication system actually is almost omnidirectional, and it can go through obstacles as long as the water is connected. And yeah, so actually, even I mean, with some nice antenna design, you can make the communication system much more stable and long distance. And with these communication systems, we integrate it and test a leader-follower performance. So basically, we have these two robots. One is a leader, and another is a follower. So by communicating between leader and the follower, so this leader robot can kind of guide the follower to follow the leader's behavior without any kind of knowledge about the environment. So the follower do not need to know anything, just follow the leader's behavior, and it can do some obstacle avoidance under the help of the communication system. So this is one example event we kind of get inspiration from the aquatic animals and developing some new kind of communication or perception systems. Some of the ongoing work we are doing is that, so in nature, fish can swim efficiently across a very wide range of speed. How they achieve that? Their strategy is that they can tuning their stiffness accordingly based on the speed profile requirement. For example, at lower speed, the fish will tend to be more soft, and at higher speed, the fish will be more stiff to kind of maintain a high efficiency. So we are kind of exploring this mechanism, how we can design some online tuning, a stiffness tuning system to kind of make sure that our robot can be able to have a maintain a very high efficiency across a wide speed profile. And basically, we have two robot prototypes. One is a robotic fish. The other one is a machinery robot. You will see these videos here. And we have two types of robots that can online tune their stiffness, and we can use this robot platform to further explore this potential or optimal strategies we should use for the stiffness tunable strategies. Another interesting work we are exploring is that the cross-domain vehicles. So this cross-domain vehicles is very interesting because it can fly different water bodies and can serve larger areas of the interest of the area. So the robot we are, or the creature we are targeting on is the flying fish. So in nature, this one fish, they can fly out of water and gliding hundreds of meters. To see this flying fish, they can speed up very fast, reach kind of more than 10 centimeter or 10 meter per second to achieve a very amazing performance. So we are studying this kind of phenomena and see whether we can kind of finally build such a platform to both swim and fly out of water, have such a cross-domain robot. And we are mostly, we have some prototype, but it's still very at the very beginning. And we are developing these cross-domain simulators, and then it have some like potential to jump part of the body to out of water, and it's some of these preliminary results. So we believe, yeah, by learning this amazing flying fish behaviors, we can kind of push the boundary of these cross-domain robots. Yeah, I guess like my main research or long-term goal is that we want to both like make our marine robot more autonomous, then make our marine or our oceans more accessible, and even we can use our marine robot to treat these marine issues, then to make our marine or oceans more green and healthier, and also with the high rise, I mean the water level of our I mean in the Earth is just increasing. So maybe most of like gradually most of the cities will disappear. So we are thinking about maybe we will building these floating cities in the future, and we a lot of us might move to these oceans and live with oceans in the future. Okay, this is pretty much to the end of my talk. I will thanks a lot for my collaborators, students, and the funding agencies. Yeah, this is of my group with graduate and undergrad, and some of the funding agencies. Okay, thank you. I guess I will take questions.
The flying fish robot would be basically for bursts of telecommunication. Just because you do it, or?
Because like when the robot can fly in the sky, it can fastly like reach to some target quickly and solve the like maybe when we do some rescue, this robot can just jump off the water and fly into the target to save some people or to rescue some people. And also a lot of times, like for example, in Madison, we have several lakes, but they are not connected. If we want to do this water monitoring, we need to move the robot from one lake to another. If this robot can kind of fly, they can kind of fly to another lake without any human intervention. Yeah.
So amphibious.
Yeah, amphibious. Yeah. Yeah.
Great talk. I think my question was in the leader-follower system.
Yes.
What is the nature of communication between the leader and the follower? Is it like what kind of messages are you passing between the people?
Basically, so as the leader is like behavior, like when it is moving forward, it will send a forward command to the follower. And if it's changed to ascending, and it will also send this ascending command to the follower. In this way, the leader or the follower can always follow the behavior of the leader to kind of do the avoidance. And there are not too many coordination so far. Or I mean, in that work, we do have some research that we have multiple robots, and under the with the help of this communication system, we can do multi-robot coordination and form some shapes. But I didn't show it here.
Yeah, so I have another question about that. So if you have, let's say, 3 robots or 4 robots,
Yes.
how would the leader send a different message with the electromagnetic system?
Yeah, that's a good question. Actually, except for this communication system, we need to design some protocols for multi-robot coordination. So we have some networking research, like how we design a networking, like a routing method for this to make sure that it didn't conflict between each other. So we don't talk about that, but we do have this kind of research for like further networking stuff for this application. Yeah.
And so to extend on that, so the follower is essentially reading the change in the electric field of the leader. And does that drop off very quickly as you?
Yeah, I mean, that's a good point. Yeah, I mean, our current communication system can reach like, or in this research I did before, it's only several meters, like 5 meters communication range. And currently the latest result can reach like 3 or 30 meters, but still it's not great compared to like this acoustic. But it can already help a lot for this small scale robotic research. I mean, our goal is that we finally want to reach these hundreds of meters, which will be make it very practical in the field, at least for some of this local coordination between robots and even humans. Yeah.
But I suppose, you know, so you're sending very small, essentially Morse code almost.
Yeah, yes.
Signals in the coordination. So, I mean, couldn't you have, I mean, acoustic signals can travel for many miles. Couldn't you have a very cheap, inexpensive thing that just basically goes ping at a certain frequency, and essentially delivers the same, you know, up, down, slow, whatever?
Yeah, maybe like I guess one very simple strategy is that we can just increase the transmitting power of the system, then it can reach much larger distance. But the thing that normally the small robot cannot kind of afford or can carry this larger power or battery system. But I mean, as you said, maybe we can set some kind of beacons or base stations for the communication. I mean, in that way, we can generate some nice network or this electrical communication based networking system for in the future to compensate the acoustic method, because this one it can communicate very fastly. Yeah, much faster than the acoustic method. So it almost can be in real time. Yeah. Thank you. Yeah.
I have a question again on the same system about the limitation. So you mentioned about like power and how you can have a less powerful transmitter, basically.
Yeah.
How small is the current in this system, and is it easily get dissipated out by the noise, or?
Yeah, I mean, currently the power consumption is about 1 watt. It's pretty low actually. Yeah, I mean, it's just a kind of get like degrade or the signal just decrease very fastly. That's the reason we can only communicate 0 meters for now. But again, like we just designed this board like by ourselves. So I guess by improving the signal noise ratio, or kind of design more professional circuit, I'm sure that we can increase the communication much larger. Yeah, but yeah, I guess that's the next step stuff.
Thank you.
Yep. Thank you. Yeah.
In your the board project,
Yeah.
what kind of sensors are you using to detect? When there's like a lot of waves and
Mhm.
stuff, what kind of sensors is there to detect like when the board drifts off the deck?
Are you talking about the like are we monitoring the disturbances or?
Yeah. How do you monitor this?
I mean, we do not directly monitor the disturbances. Like we just using this neural network to learn from the error to kind of indirectly estimate the disturbances and also the model accuracy together. So I mean, I think like if we can use neural network to learn or predict the waves or this current in a more expressive ways, it's also a very interesting kind of topic. Yeah. Thank you. Yeah.
Great talk. So I just have a kind of simple question. So how does this robot navigate? I do talk about LiDAR, but do you have some other system for them to navigate?
Yeah, so I mean, in this coastal area, we basically use LiDAR and MU to generate a SLAM and a real-time map. We are also integrating this GPS and also DVL together to make sure that our perception and localization is more stable. Not sure whether I answered your question.
Sure.
Yeah, like basically we will integrate, and also the cameras.
Okay.
Yeah, we are also integrating camera to kind of get more kind of robust SLAM and perception. Like we're combining both camera and the LiDAR data together to get more robust localization system.
And also for the small robot, same.
No, for small robots, we mainly use the camera and some MU. And if we want to test in the field, we will integrate the GPS again, but not LiDAR for LiDAR. So for the small robot, it cannot afford this high computing resources of this LiDAR system. Yeah. Yep.
So for the boat system,
Yeah.
because you have used some sort of learning to help you
Mhm.
bridge the gap for the model. What happens when people walk on them? Do you have data for that or is that something you just?
I mean, that's a good question. I mean, for this current research, we didn't test the payload stuff, but we have another piece of work, like we developed a adaptive controller that when we transport people or have payload, it can perform well. But I mean, even we didn't test it, I think this system should be worthwhile with payload on board or change of payload, because like if you see the formulation, this neural network will learn the model inaccuracy in real time. So yeah, I believe it should be working well. But I mean, anyway, we need to test to give a more conclusive answer. Thank you. Yep.
I guess some optical wavelengths will penetrate through at least a decent amount of water better. That's.
Uh-huh.
So you wouldn't think of like using some kind of combined optical and electronic and electric field thing? I mean, what do you see as the advantages of the electric field? Is it just that it gets around obstacles or?
So your question is
Can the
how
underwater communicate?
So you are asking about whether we should integrate with other modality of communication or maybe like I guess it has the limitations, like it normally cannot like reach a longer distance, so we might need to like using acoustic for longer distance communication, and even maybe in some clean waters, optical communication is also very nice solution. So we can kind of combine the two together, or even like maybe this light-based communication will have I guess I mean there are some possibility of integrating these two systems and make I mean they should be on board together to kind of have a more stable and reliable communication for the underwater vehicles. Yeah, and also actually this electrical communication system, they can be also used for obstacle detection. Like at land, you can detect the the change of the electrical field or distortion of the electrical field. You can identify where is the obstacle actually. We have some kind of this research, but I didn't talk here. Yeah. Yeah.
And so the flying fish just strike me as being really neat.
Yeah.
I mean, presumably, if you could coordinate flying, then you could have, faster communication above the water and go back into the water. Could you even like relay up to a satellite from your flying fish?
Yeah, maybe that's an interesting point.
Yeah, GPS.
Yeah, I guess that's a good point. Like maybe we can kind of fly off the water and get a kind of treatment, or not to, I mean, get a calibration of the position and then jump into the water again. In this way to kind of have always like a benchmark or a recalculation about the localization system. Yeah, that's a good thought. Thank you.
All right, it's 4 p.m. Let's